Hi, my name is Ziming Li from Rochester Institute of Technology. I'm going to present our work entitled Exploring Large Language Model-Driven Agent for Environment-Aware Spatial Interaction and Conversations in Virtual Reality Roleplay Scenarios. Previous large language model-driven VR agents for communication training have primarily focused on roleplay conversation simulations. However, these VR agents remain static. Previous studies suggest integrating elements such as hand-based interactions, movement, and context-rich environment into VR agents to create more realistic hands-on skills training simulations and improve knowledge transfer. Previous work have investigated using large language model-driven agents to simulate lifelike activities and develop conversations, as well as perceive and interact with environmental objects. However, it remains unknown regarding the validity of large language model agents in VR, involving conversations and objects handling within the scene, especially for roleplay scenario simulations. Thus, in our work, we aim to investigate two research questions. First, how can information about virtual environments and user interactions be effectively communicated to a large language model agent using text prompt? Second, what is the large language model agent viability and task performance in generating environment-aware spatial interaction and conversations in role-play scenarios based on perceived environmental informations and users' inputs? We identify 6 key components in VR scenarios based on previous setup in role-play scenario simulations. Adding interactions such as hand-based actions and movements, and interaction contexts such as objects and characters. To convey these key elements, we define a schema with 5 main components, including system context, spots, objects, characters, and communication. These components provide the necessary contextual information for role-play scenario in the VR environment. Specifically, in the function list within the system context, we define a list of hand-based actions with objects for the agents, including grabbing, releasing, poking, and pointing. The function list also includes agents' movement cues, and the spots component defines different locations for the agent to move within the scene. The object component defines objects which are classified as containers or non-containers, and also as fixed objects or movable objects based on their characteristic within the scenarios, which help agents understand spatial relationship and perform actions in the environments. Using this schema, we systematically define the structure of the context prompt, which informs the agent's communication cues and interaction within the VR environments. We develop a plugin in Unity game engine to convey different elements within the VR scene into the prompting schema to communicate with the large language model agents and simulate different roleplay experiences. To evaluate this schema and agents' behaviors, we develop 5 scenarios. In the first scenario is the fruits and vegetable store, where the player will be acting as the counter staff member and the agents will be acting as a first-time customer. Here, the agent will collect the items like different vegetables and fruits and put them into the baskets and head to the checkout. The second scenario is the convenience store, where the player is the customer and the agents will be acting as the counter staff. In this scenario, the agents will orally help the player to locate an item from the shelf, so the player can collect the items they wish to purchase and head to checkout. The third scenario is the art gallery, where the agents will be acting as the tour guide and leading the player around this art gallery and introduce different items such as the sculpture and the painting. The fourth scenario is the game room, where the agents and the player are playing a move and guess game. Here, either the agents or the player are taking turns to move the objects between the baskets, and their playmate will guess which item have been moved between the baskets while they are turning around. The fifth scenario is the fast food store, where the agent will acting as the counter staff member and the player will be acting as a customer who will ordering items by pointing at the menu board. So the agent will collect all the food ordered by the player. Here is the demo of this fast food store scenario. The player is ordering the giant burger by pointing at the menu board.
Absolutely. That's our giant burger. It comes with 2 beef patties, quite filling and a favorite among many of our customers. It's priced at $4 each. Would you like to order one?
Once confirmed by the player, the agents will head to the shelf and collect the burger which just ordered by the player. And then it will head back to the counter and put the burger to the tray to simulate this kind of ordering experience. To evaluate the agent behaviors, we conduct a user study with 14 participants. During the user study, the participant can freely interact and develop conversations with agents and scenes based on given tasks and goal. The participant will experience 5 scenarios in a counterbalance order. We identify some key findings from the user study. First, we identify the agent can localize objects, interact based on object characteristic, respond to user cues such as movement, pointing, relocate object, and maintain character roles. For example, in the fruits and vegetables store scenario, we identify the agent can plan interaction based on object characteristic, where the agent avoid placing watermelons into shopping basket when instructed to do so. In the fast food store scenario, we identify the agent can respond to participants' contextual pointing cues. Here, the participants pointing at a list of items, and the agents can successfully interpret this interaction. We also identify the agent occasionally hallucinated objects which are not defined in the prompting schema. For example, in the convenience store scenario, they accidentally saying there's a back wall which is not defined in the schema. We also identify agents occasionally slows response time and the need for user to frequently initiate interactions, especially while performing complex multi-step tasks. These challenges can impact agent responsiveness and users' experiences. While most response latency can be attributed to large language model processing, network transmission delays, and our system processing time, participants occasionally experience a noticeable lag when the agents will tend to generate valid response when indicated by our feedback system. For more details, please feel free to refer to our paper. Thank you for listening.